Now, I don't really want to spend a lot of time on the Heisenberg spin chain. The only thing I want to emphasize is the fact that the Heisenberg spin chain's phase transition and the helium-1, helium-2 phase transition shares the same kind of critical exponents. Thing which looks like an angle. They could share similar kind of order parameters. That's why their behavior is so similar. We're talking about, in particular, helium-2. We are essentially talking about somehow having macroscopic quantum behavior. So basically something which you should be able to describe by a wave function. Now, this also that I need. Okay, I'm back. And you did hear that helium-2 must have an angle somewhere in its description, right? In order to ensure that it would essentially have the same the Heisenberg spin chain. Being quantum. Would it?
So we cannot hear you.
Okay. Can you hear me now?
Yes, sir.
I've changed the network. Hopefully, this will not cause the same problems as before. Let's see. The question we were asking is in helium-2, where is the angle? You understand why the question is important. In the description of Heisenberg spin chain, an angle is basically the order parameter. Helium-2 must also have the same kind of order parameter which distinguishes helium-2 from helium-1. An order parameter is something which essentially is zero in one phase and has a non-zero value in the other phase, indicating that the phase transition has occurred. A sudden jump or a change in the order parameter would tell you that. Okay? So, question, helium-2 has a wave function, right? It should have a wave function description because we expect it to be quantum behavior shown at a macroscopic scale. But in a wave function, how do you fit in an angle? Something which behaves like an angle? That's the question that I was asking you. The answer is very simple.
Phase.
Yeah, exactly. The wave function is a complex number in general, and it actually has a phase. So what Landau did was essentially assume that you can describe the superfluid part, just the superfluid part of helium-2. Remember, two-fluid model, helium-2 is composed of a normal fluid and a superfluid. He assumed that the superfluid part could be actually described by a wave function which looks like this.
So you did not share the screen.
Thank you. Forgot I just sharing stuff when I left. Okay, so this was Landau's assumption about the way in which the wave function should behave. This is pretty straightforward. You are saying that the superfluid wave function, this is not the wave function for a one particle, is a wave function for the entire collection of the system. Or you could say every particle is in this system essentially is in the same state, so they share the same wave function. This is the real part. Why have I called the square root of n? Because chi mod square will be nr. So that's part of the probability interpretation. And it is I theta r. This theta r is the phase. We are now talking about a static situation. Let's assume that the superfluid is stationary for the time being, it's not moving. If that happens, then all these things will be time independent. Or actually, okay, let's do it in full. There should also be time dependence in general, right? So psi s should be a function of r and t, superconducting wave function, and it will have a magnitude which is related to the density, and it has a phase. And it's this phase which will be critical in the phase transition. Now, let us take a look at what the physical significance of this phase will be. So if you have a wave function which changes with time, of course, the probability density at a particular position might change with time. But how can the probability density change? Can change only because the probability is flowing out from the surface of the region. This is called the local conservation of probability. Just like local conservation of charge, charge in a region can increase or decrease, but it can change only if it's flowing out from the surface, right? So the equation which describes that, what is that called? The equations which describe local conservation of any current quantity, like say charge density changes in a region, that's essentially because there is a current flowing out. Remember what that equation was? Connecting charge density and current?
Minus IH cross by 2m psi star grad psi.
Oh,
Minus psi.
okay, good. You're talking about the probability current density directly, right? Fine. Then minus I cross square by 12. Then
Minus IH cross by 2m psi star grad psi. Psi star grad psi. Minus psi grad psi star.
what is this quantity?
Current
You're
density.
right. This is which density?
Current density.
This is the current density. Probability current density to be more precise. And of course, the actual current density is psi star psi, which in this case is obviously n, right? Now, if I take an expression like this, and try to find out J from there. It looks like a non-trivial task because there's a lot of things which depend on R, but you have to also remember that this thing, this is a conjugate of this, right? So when you subtract a number from its conjugate, what do you get? Do you get a real number or an imaginary number? Or a complex number? Psi star grad psi and psi grad psi star are conjugates of each other, right? Is it okay?
Yes, sir.
So what's the difference? What kind of a number is the difference? You subtract the complex conjugate of number from itself. What do you get? The number z equal to x plus iy has a conjugate given by x minus iy, right? So if you subtract the two, you get twice iy, which is 2i times the imaginary part. Okay? Elementary complex numbers. And therefore, note that this minus I by 2 exactly cancels the factor of 2i. So what you have is h cross by n, imaginary part of psi star grad psi, right? That's another expression for J, equally useful, perhaps. Okay? Now, if I try to calculate this, if you want to calculate grad psi, note that psi is a product of two things. So, when you take a gradient, you basically get gradient of square root of n to the I theta. I'm not writing in function of r and t. That's understood? Plus square root of n I grad theta into the I theta. Is that okay? Now, if you gradient of square root of n, that looks like a bit of a nasty quantity. But note that if you multiply psi by psi star, e to the minus I theta will cancel e to the I theta out, right? So what will you get? You will get root n, grad root n. Still looking very nasty here. That's I n, because it's root n times root n now, grad theta. Okay? What makes life very easy for us is psi star grad psi's imaginary part, which is what you need in J. It's actually very simple, isn't it? It's just this. Please let me know if you are finding any step difficult to follow, because then later things will become even more complicated. But you do realize that the imaginary part, which is what you need here, is just this. So J vector just turns out to be h cross by m n grad theta, where n is the density, right? N is the probability density, J is the probability current. Again, all of this is for the superfluid, something which is being treated like every particle in the superfluid is in a single quantum state. And the wave function is of that state. So far, everything is okay? Obviously, a question like that means that if you have a problem at any stage, please ask. But now, can anybody tell me what is the connection between current and density? Is there a connection at all? This connection is not, I'm not talking about this formula. I'm saying there's a very elementary connection between the density of an object and its current. Something which I even mentioned the last day when we talked about two-fluid model and the current in two-fluid model. This is, of course, not correct. What is the correct expression?
J equals NV.
Right. In particular, this is the superfluid part. So this is Js equals NVS, right? And this immediately tells us that you can relate the theta, or rather its gradient, with a purely physical quantity, right? The velocity of the superfluid is actually given by h cross by n grad theta. Okay. Note that it is the rate at which theta changes from point to point, which is related to the physical quantity, not theta itself. Which is of course great because you all know that theta is not perfectly well defined. Theta can change theta by 2 pi and still talk of the same function, right? So theta directly should not have had a connection with a physical entity. That would have essentially told you a physical entity could jump around by 2 pi or multiples of 2 pi anything. But that doesn't happen here. Here is gradient of theta, which is of course something which, even if you were to change theta by 2 pi, gradient of theta would stay the same. Okay. So the all-important result which we have here is the superfluid flow is connected to the phase of the wave function by this particular relationship. But what is very important is the superfluid flow velocity is a gradient. So what is so if a vector or a vector field rather is a gradient of a scalar field, what immediate property does it have? And what is such a field called? If V is gradient of something, which it is in this case, what is the property that it has and what is this property's name? Yes?
Scalar field.
Sorry, I
No,
couldn't hear
another.
you. Solenoidal.
Solenoidal.
Well, solenoidal vector field is called solenoidal because it shares the same property as the magnetic field, as something which a solenoid causes, which is of course a magnetic field. But the magnetic field is not the gradient of a scalar usually. The property of the magnetic field which gives solenoidal vector field this name is that the divergence of B is zero. Any field with zero divergence is called solenoidal. This field doesn't have zero divergence, right? What does it have? It has zero curl,
Solenoidal.
right? Being a gradient, it has zero curl. Okay? And the name of this kind of field is the other kind, not the solenoid.
So rotational.
It's irrotational, not rotation.
Is
It's called irrotational simply because zero curl would sort of go against a rotating thing. A rotating thing would actually have a non-zero curl. In particular, if the curl is zero, then this quantity, kappa, which is this, the line integral of the superfluid velocity along any imaginary contour whatsoever, how much will this be? Yes, for a zero curl thing,
0.
it should be zero because Stokes' theorem would tell us that you should be able to change this to the integral of curl of ds dot ds. And this integral is to be done over a surface whose boundary is this loop gamma. And since curl ds is zero, you should get zero. So this is the result, which irrotationally means, and this quantity is called circulation. Essentially, calculates how much of the liquid is spinning around. This should be familiar from elementary vector analysis, right? So circulation of this velocity field should be zero, which means we would not expect, at least on the face of it, we should not expect a flow like this. If you have a flow like this, then of course, if you imagine the loop which goes like this, V and dl would be parallel throughout. You will always get positive contributions. So of course, you cannot get a circulation of zero. Do you understand that? If the circulation is zero, a flow like this should not happen. So superfluid should not spin around. At least that's what it looks like. right? Is that okay?
Yes, sir.
In particular, one kind of flow which you often see in a liquid, suppose I put a liquid in a cylinder and then spin the whole thing about its axis. The cylinder is spinning, but what would happen is the superfluid or the fluid close to it could have started spinning and moving with it. And in a normal liquid, that actually happens. The liquid turns around, and as a result, the surface essentially bulges out into a parabola. This is familiar, right? If I'm a spinning fluid, the spinning fluid has a surface which bulges out like a parabola simply because then it's possible for you to get enough centripetal force to make the fluid keep on spinning at every point. In fact, this is very important. Even technologically, people produce mirrors of large telescopes by, say, having a pool of mercury and making it spin. And you get a perfect parabolic mirror. Now, this thing should not happen for a superfluid because if this happened, you would have a V equal to omega cross R. You know this, right? If everything were spinning together with an angular velocity omega, the speed would be omega cross R. And then you can easily calculate the curl of V. Okay, that's a homework. Work it out yourself. And you should get twice omega, which is, of course, not zero. So, a superfluid moving as a whole cannot really exist, at least. You should not expect a superfluid to flow like this, every portion moving in the whole, as a whole. Okay? All of this follows from the fact that the superfluid velocity is a irrotational vector field. However, let me point out one situation when superfluids can very well flow. Suppose you had these two walls. So you have a region between two cylindrical shells and the superfluid says here, in between. Okay? Now, if you calculate the circulation, you can get a non-zero circulation. Now, why is that the case? How do you escape this particular form? Can you tell me that? Experimentally, you will find that superfluid can be made to spin between two cylindrical shells like this. And even theoretically, that's not a problem. But why is that not a problem? If this liquid is going round like this, then it should have a non-zero circulation on a loop like this, right? A loop which goes to a superfluid will find non-zero circulation. Didn't we just prove that circulation would have to be zero? Did we prove it or not?
Yes, sir.
Okay. But however, notice that in this proof, what did we use? This was the circulation gamma through this loop gamma, right? Here, the loop gamma is basically some closed loop which I'm taking here between the two cylinders. And the circulation in this loop is equal to the integral of curl of Vs or ds in a surface which is bounded by the loop, right? But is curl of V zero everywhere in the region bounded by the loop? Where is the curl of V zero? Curl of V is zero for the superfluid, right? If you have a region like, have a setup like this, two concentric cylinders, coaxial cylinders, with superfluid between them, then for this surface sigma, which could be, for example, this flat surface, Vs is not even defined everywhere, right? It's defined only where the superfluid is. is not defined in this entire region. Do you understand that point? For example, it's not even defined inside this hole, the region inside the inner cylinder. In other words, this formula simply cannot be used because curl of Vs is not available to you over this entire cylinder or entire surface bounded by the loop. Okay. Why is this equal to 0? Why was this equal to 0? Because curl of Vs was 0 everywhere on sigma. Why? Because everywhere on sigma you had a superfluid. Here you don't even have a superfluid in the region internally. So it can't, so Vs is not even defined, curl of Vs is not defined there. So this proof would actually break down. Clear? Yes?
Yes, sir.
In fact, you can actually calculate how much circulation will be just starting from the expression that we have actually obtained. Remember? This was Vs, right? So this integral actually can be done trivially. Can't it? What is grad theta dot dl? I'm not talking about what is grad theta dot dl in this particular case. I'm saying in general, if you take the gradient of a scalar dotted with displacement, that is dxi plus dyj plus dzk, what are you going to get? Theta, of course, is component like del theta del x. But when you dot it with dxi, you get this. Do you recognize what this thing is? You should know this because that's how you define the gradient in the first place. What's that quantity?
Delta theta.
It's actually d theta or delta theta. This one is just a differential of theta, which is a function of x, y, and z. So this thing is d theta. And h cross by n is just a constant. So what is delta theta is the integral. When you integrate over d theta over a loop or any region, what you get is delta theta, which is a change in theta from one end of the integration line to the other. In this case, the integration line happens to be a loop. So it's really the change in theta when you go all the way down and return at the same point. But now comes a very important point. The wave function is singular value. So when you come back to the same point, the wave function should have the same value. That shouldn't change. So what does it tell you about delta theta? Remember, psi, the wave function is square root n into the I theta. You expect psi to return to its same value when you have gone all the way around. And here you are asking how much does theta change when you do that? So what's your answer to that?
Between 0 to 2.
Between 0 to
2 pi.
actually come exactly not. That's the one thing that can never happen. Remember, you're back to the same value. Whatever value you started with, you're back to the same value. Psi has to be the same. Psi, which is square root of n into the I theta, has to be the same when you go all the way down the loop. Let's say you start here, you go all the way down, come back here. You don't have two values of psi at a particular point. So psi has to be the same value. Root n, the magnitude of psi has to be the same value. So if this had been delta root n, that would have given you 0. But why is delta theta allowed to be non-zero? And how much can it be? Come on. Just forget wave functions, forget everything. It's a complex number. How much can its argument change? Or can it at all change? Might be that it cannot at all change. But how much can the argument of a wave function of a complex number change when you are back to the same value for that complex number? Is it possible for the angle to change at all? In other words, what I am saying is it was root over e to the I n I e to the I theta to begin with. In the end, it's root over n prime into the I theta prime. But it must be the same, right? We're back at the same point. So what can you say about the connection between n and n prime and theta prime? If this is true, then let's ask a simpler question. If the complex number were written in terms of real and imaginary parts, and two complex numbers obeyed this, what would your conclusion be about x?
Sir,
Hmm?
sir, x is equal to x prime and y is equal to y prime.
Right. This is basically how you talk about equality in the Cartesian system, so to speak, in the real part imaginary part system. This basically is a polar form. Root n is just the magnitude, right? So it's rho into the I theta equal to rho prime into the I theta prime. So what is the connection here? N prime and theta prime. What's the relationship between them? Does n have to be equal to n prime? So you gave me exactly the right answer when the complex number was written in terms of real and imaginary parts. But you all know that this is the other way of writing a complex number. Magnitude into e to the power I thing, right? In that way of writing things, what is the condition for equality? Do we have n equal to n prime? And do we have theta equal to theta prime? Do we have both? Do we have one of them? Or none of them? Again, nothing to do with superfluidity or even quantum mechanics. This is just plain quantum complex number theory. Yes? So this is the more familiar form in which I could write this. What does this tell you about r and theta? Here r is actually square root n and r prime is square root n prime. Yes? Tell me.
So they'll be equal.
Which one? Both of them? Of course, one obvious thing is if both of them are equal, n equals n prime and theta equals theta prime, then these two have to be equal. But do they have to be? N equal to n
Theta
prime actually
prime is
has to
equal
be.
to theta plus
So,
2 and pi.
theta actually could differ from theta prime, or theta prime could differ from theta. It doesn't have to be equal, but has to be some multiple of 2 pi. I'm not going to call this 2 pi n because I've already used this n. So let's call the 2 pi p, let's say. Where p is some integer. 0 is possible, 2 pi times 0. But it can be 2 pi, 4 pi, 6 pi, 8 pi. You all know this, right? When the wave function returns, when the point returns to its own value, the wave function has to come back to the same value. And because of that, theta can change, but can change only by multiples of 2 pi. The magnitude cannot change. The magnitude you can calculate by, remember the magnitude is simply square root of psi times psi star. If psi is the same before and after going through the whole loop, psi star also has to be the same. So psi and psi star's product will not be the difference. So n cannot be different from n prime. But e to the I theta equals e to the I theta prime does not mean that theta equals theta prime because if the I 2 pi times any integer is 1. Well, this is trivial, you know this, right? But what does this tell you about circulation here? You're going all the way round the loop and coming back to the same point, right? So what can the circulation be? delta theta. How much can the change in theta be? Change in theta is simply theta minus theta prime. How much can that be? It's written here. It has to be 2 pi times an integer. In other words, circulation, the flow of fluid in a situation like this, flow of superfluid, cannot occur in any amounts. It has to occur in such a way that the circulation is this basic unit, Planck constant H note, not H bar, over M. That's the basic unit. It can be multiples of that. Okay? So this is called flow quantization. This should remind you of something you must have studied about in superconductivity in your previous course, something called flux quantization, which happens in superconductivity. Have you read about it? Flux quantizations and superconducting vortices and so on. Yes or no? So this is basically analogous to that. Not the same thing, but again, there also you have a superconducting wave function, which is a macroscopic wave function. And that macroscopic wave function, the space part, it leads to flux quantization. Here, this leads directly to flow quantization. The superfluid flow, when it's spinning around, cannot have any circulation, can only have circulations which are integer multiples of this basic unit h by m. Okay? Now let us go back to this question about a superfluid in a cylinder, and I'm making the cylinder spin. We argued that because circulation, there on the other hand, notice one thing, there on the face of it, if you had a full cylinder, you would think that if you take any loop and try to calculate circulation through that, you would have to actually calculate the surface integral over a surface bounded by this loop, which would mean Vs would have zero curl everywhere. There is a superfluid in this whole region. This is not a superfluid between in an annular region between two cylinders. It's a superfluid which is in a solid cylindrical volume. So the loop has superfluid in it. Curl of Vs is zero everywhere. You should have zero circulation. Is that okay? Yes?
Yes, sir.
So we would expect superfluid, at least you might always say, okay, superfluid will not flow, but then you do have a normal fluid that will flow. But let's say even at temperatures very near to 0 Kelvin, it is almost entirely superfluid, there you would expect no such circulation because this is entirely solid. Solid meaning the loop has superfluid everywhere, curl of V is zero everywhere. However, it turns out that you actually will get circulation in a rather special way. You will not get the liquid to flow like this. But what you will do is, inside the body of this whole fluid, you will find tiny vortices where the fluid is spinning around. You will find another tiny vortex here. And lots of tiny vortices, in fact. Okay? This is what you will find. The question is, how is that even possible? Because no matter how small this region is, if you have liquid going around like this in a small loop, that will definitely have a non-zero circulation. So how do you beat Stokes' theorem here? You still remember Ps is h cross by m grad theta. And therefore, kappa, the circulation, has to be h cross by m delta theta. That's what we have figured out, and hence has to be h. H by m times an integer, which we call p. But this also tells you that curl of Vs is 0, and that tells you that if this curl of Vs is zero everywhere in a region bounded by a loop, circulation had better be zero. But if you have fluid flowing like this somewhere, circulation cannot be zero there. So any vortex like this, anything which is spinning around, looks like it's a contradiction to this curl of Vs equal to zero. But vortices actually can exist. And the reason for that is simple. The reason is that the superfluid is not a continuous medium, right? You understand why what I'm talking about? At least at the very center of the vortex, you have no fluid, right? You have a zero size point, which means if there's a helium atom there, there's no helium atom in its immediate vicinity. The other helium atoms have to be distant from it. Far away, actually, but not far away in macroscopic terms. Macroscopic terms is a very tiny distance away. But in the microscopic world, what you have is you have spinning regions of liquid where there's a gap in the middle. Because of the presence of a atom there, or helium atom or a helium molecule, whatever you call it, there you don't have fluid at all. You have a gap. The fluid part is, of course, something where you are making a approximation. You are coarse graining type of thing. When you say infinitesimal in the physics language, for situations like this, it doesn't really mean infinitesimal. It means a small enough region that you have that is very, very tiny according to your daily life world, but it's actually uh, it's very tiny according to your daily life world, but at the same time, it's huge compared to the microscopic world. You have many, many molecules in there. But all such situations would have regions in between where you do not have fluid at all, simply because you can't have a fluid everywhere. The finite volume of the molecules prevent that. And since Vs is not defined there, curl of Vs is simply not defined, and you again can get a non-zero circulation. So the non-zero circulation in an annular region between two cylinders was possible because physically there was no superfluid inside the inner cylinder. Here you can have small vortices near microscopic vortices or very tiny vortices anyway. But these are allowed simply because at the center of these vortices, you have a gap where there is no fluid, no Vs, and hence no curl of Vs. Okay, and so the Stokes theorem calculation breaks down. Got it? So this is how you can have spinning vortices inside a superfluid. Any questions so far? Tell me. Okay, if not, let us now try to take a look at this superfluid vortex in a bit more detail and try to understand what's going on inside. At least try to figure out how the velocity will change as we move away from the center of the vortex and so on. So basically what you have to do is you have to solve the basic equation that curl of Vs is zero. For a flow like this, and try to see what this says to us about the flow. Once again, this looks like a contradiction in terms immediately because curl of Vs is zero looks like implying the circulation is zero. It doesn't have to. It only tells you the circulation has to be h by m times an integer. If the superfluid had been continuous, existing everywhere inside this loop, it would have given you zero, but it's not continuous. There are tiny cores of the vortex where you don't have fluid at all. Okay, now we want to do some want to do a bit more mathematics to figure out how Vs depends on the distance from the center of the vortex. But given the symmetry of the system, what kind of coordinate system do you think would be best to use? You want to solve an equation like curl of Vs equals 0. Okay. But first of all, you may get infinitely many solutions. But apart from that issue, what I'm really concerned about here is if I use a bad coordinate system, bad for this particular thing, the equations involved may be way too difficult to handle. So by looking at the symmetry of the system, you should be able to decide what kind of coordinate system would be best to use. Yes?
Symmetrical.
Yeah, cylindrical polar coordinate system would be the best because you have an axis and you have cylindrical symmetrical flow around that. So you need to be able to work out this in the ER, E theta, E phi, ER, E phi, EZ system. Okay, you all know what the cylindrical polar coordinate system is, right? It's basically like the polar coordinate system with a Z added to it. The curl of Vs in this coordinate system has this particular form. It's ER, R E phi, Ez. Is a standard determinant, but cylindrical polar you may not remember. So these are the derivatives that's in. And your VR, RV phi, and VZ. Where VR, V phi, VZ are the components of V. Now, just one question. Is this going to give me the right dimension? Can this even be correct? Yes. Is it even dimensionally correct? Let's look at one of the terms. One of the terms will be this into this into this, or not really into, but ER del phi VZ. This is the correct dimension for curl of V. What is the dimension of curl of V? In curl of V, you're basically doing an XYZ derivative. In this case, R theta phi derivative, but in the Cartesian coordinate system, you would be doing things like del X of Vy, etc. So what's the dimension of that? Yes. Am I still connected? This is a very trivial question, right? V is the velocity. Curl of V, what is the dimension of that? Yes. Come on. Curl is the derivative. So dx dt. What is the dimension of this quantity? Where x is position and t is time. What's the dimension of this? You know what that is, right? Well, you all know what the dimension of this is. This is the velocity. What's the dimension of velocity? Am I not connected or are you not being able to hear me? Yes? Tell me whether I'm connected or not. I seem to be. Okay, it seems that many of you got disconnected. Do you hear me actually? Hello?
Yes, sir.
So, the question was, what is the dimension of dx dt? All of you know that, right? Dimension of velocity, what is that? This should be familiar, right? L by t, length by time. A derivative may involve complicated calculations, but ultimately it's basically find the change in position, find the change in time, divide the two. It's basically a division of a position by a time. So you must have LT inverse. So I was asking, what is the dimension of this? The curl is a space derivative, right? It may be a complicated combination of space derivatives, but it's still a space derivative. Yes, I'm expecting an answer about this. What is the dimension of this quantity? Where Vs I know is its velocity, so as dimensions LT inverse. What's the dimension of this, and is the dimension of this quantity the same? This is really elementary. I'm not asking you something difficult, actually. So don't think of very complicated things. Yes. Is this something which you're not familiar with? Units and dimensions should be the first chapter of any physics book. Oh, I think everybody's gone. Is there a problem with the connection out there? Yes. No, are you facing a problem with connections? Because it seems that everybody is going out and coming back in.
Yes, sir. There is some network issue here.
This
Actually,
seems to
it's
be not
raining outside.
okay. Today the issue is not here. Actually, this issue is not at my end. Because I now, at least for a change, I have a rather stable network. Yeah, it's raining in Calcutta, right? Maybe
Yes,
that's
sir.
okay. But now that you're back, you tell me what the dimension of curl of V is. Or are you gone again? And so almost everybody drop out. Okay, if it's really that difficult today, let's call it a day today. We will talk about this again later, right? Because it seems that most of you are having difficulty connecting. Now that my line is stable, it seems to be a difficult at your end now. Yeah, is that what we should do? Stop today and pick up the next time we talk about this? I'm not even sure if anybody's around to respond to this.